Welcome to the AI Checkpoints, your essential guide to understanding the latest and most impactful breakthroughs in artificial intelligence. Today, we're embarking on a deep dive into a topic that's not just crucial for the future of AI, but really fascinating. It's the quest for truly autonomous agents capable of performing what we call deep research. We're talking about AI that can independently sift through mountains of information, connect subtle dots, and then deliver profound insights, much like, a seasoned human expert would.
Indeed. And while we've seen some truly impressive feats from proprietary systems, those powerful closed-source AIs from the big tech players, there's been a noticeable gap, a frustrating chasm, really, between their advanced capabilities and what's generally available in the open source world.
Right.
So our focus today is to unpack a pretty groundbreaking paper. It's titled WebSailor-V2, Bridging the Chasm to Proprietary Agents via Synthetic Data and Scalable Reinforcement Learning. This comes from Quan Li and colleagues at Tangi Lab, which is part of the Alibaba group.
Okay, let's unpack this then. Our mission for this deep dive is to really grasp how WebSailor-V2 is engineered to shrink that formidable performance gap. We want to explore their ingenious approach to both data generation and agent training, and, maybe most remarkably, uncover why their relatively modest 30 billion parameter model is punching far, far above its weight. Kind of lightweight contender knocking out heavyweights, maybe?
That's a good way to put it, yeah. The overarching pursuit of artificial general intelligence, AGI, which is, AI capable of human-level cognitive tasks across a broad range of domains. Well, it sees these autonomous AI agents as a critical milestone. These deep research agents, they aren't just glorified search engines. They're designed to actively use external tools, browsers, search engines, academic databases even, to conduct complex, multi-step investigations. They need to understand intent, formulate queries, parse results, synthesize findings, and iterate, just like a human researcher.
Right, a lot involved.
Exactly. But for open-source solutions, the path to building such capable agents has been anything but smooth.
So what does this actually mean for us, for people using these tools? You might have noticed that your favorite open source AI assistant, for all its cleverness, maybe can't quite keep up with the deep investigative power of the big players. Say, OpenAI's DeepResearch. The authors of this WebSailor-V2 paper, Quan Li and the team, they pinpoint two fundamental challenges that have historically held things back. First up, data. Data. They observed that existing training data, it often suffers from a lack of diversity. And it operates on a rather narrow, sort of simplistic definition of uncertainty.
That's key. Think about it. Real-world research isn't just about finding a slightly hidden keyword. Right?
Yeah.
It's about grappling with complex, nuanced relationships, interpreting incomplete information, sometimes even reconciling contradictory sources. If the training data is too clean, too linear, too straightforward, the model just can't generalize. It can't handle the messy, ambiguous landscape of actual human inquiry.
Yeah, it's like trying to teach a detective to solve mysteries only by giving them these perfectly organized case files, all the clues neatly labeled. Doesn't work in the real world.
Precisely. And the second big challenge, it revolves around the training process itself. Imagine trying to train, say, hundreds of these virtual research assistants all at the same time, each needing to interact with the whole internet.
Wow. Logistically, that sounds huge.
It's immense. You're dealing with the sheer computational cost, for one. Then there's the unpredictable latency of web tools, inevitable API failures, wildly inconsistent outputs from different online sources. All these factors make scalable reinforcement learning, or RL, where the AI learns by trial and error, incredibly difficult and expensive.
Right. It sounds like trying to teach someone to drive using a car that keeps breaking down, but not just on a quiet road, like in the middle of rush hour traffic.
Exactly. And this constant barrage of unreliable or, let's say, contaminated data during training can seriously degrade the intelligent policies the AI is trying to learn. It can teach it bad habits or make it overly cautious, maybe.
Okay, so that sets the stage. Big challenges on both the data side and the training side. But this is where it gets really interesting, right? Where the Tangi Lab team comes in. They didn't just tweak an existing system or patch up a few problems. They built a complete end-to-end post-training pipeline designed specifically to tackle these foundational issues head-on.
That's right. Their methodology really hinges on two pivotal innovations. The first, on the data front, is their novel approach to synthetic data generation. They call it SailorFog QA-V2.
SailorFog. Okay.
Yeah. Now, most conventional methods for generating training data often create what you might call tree-like information structures. Think of a straightforward linear path of discovery. One fact leads to the next branch.
Simple branching.
Right. But as we know, real-world knowledge isn't usually that tidy. It's much more like a dense, interconnected, sometimes chaotic web.
Mm-hmm.
WebSailor-V2 directly addresses this. It actively constructs these intricate knowledge graphs that feature much more complex, even cyclic relationships. This means information can loop back, it can reinforce itself, or have these intricate, nonlinear dependencies.
Oh, okay. So information isn't just a one-way street. It can circle back.
Exactly. And by immersing the AI in this kind of data, it learns to navigate a far more realistic and ambiguous knowledge landscape right from the start.
So if I'm getting this right, they're not just giving the AI more facts, they're giving it smarter facts. Facts presented in a way that forces it to think more deeply, to understand context and relationships. It's like teaching that detective not just to find clues, but to figure out how those clues interrelate, even when they seem contradictory or incomplete, building a whole narrative, not just checking boxes.
Precisely. And alongside this structural complexity, SailorFog QAV2 also introduces a much broader, more sophisticated variety of uncertainty definitions. It goes beyond just simple obfuscation, like making keywords vague. They challenge the agent with nuances that require genuine contextual inference, hypothesis verification, a deep understanding of logical inconsistencies.
Things that require actual reasoning.
Yes. This really prepares the agent for the kind of ambiguity inherent in authentic, real-world research, where answers aren't always just sitting there, explicitly stated. They have to be derived through deduction, through cross-referencing.
That makes total sense. So the key insight is you can't simplify the world for the AI if you want it to be capable. You have to immerse it in the ambiguity it will face, make the data itself the training ground. But with these complex cyclic relationships and all this uncertainty, were there specific challenges, like making sure the model didn't just get stuck going in circles or completely misunderstand ambiguous stuff?
That's a very good question.
Mhm.
Yeah, they had to develop sophisticated reward mechanisms within their RL framework, things that would penalize logical inconsistencies, for example, and reward successful navigation through these complex graphs. It wasn't just about finding an answer, but finding a logically sound one. This continuous refinement, guided by these nuanced reward signals, help the agent learn to untangle those complex dependencies.
Fascinating. Okay. So, with such intelligently structured data guiding the agent, the next huge challenge was, well, how do you effectively train it in an environment as vast and unpredictable as the web? How did they handle that?
Right. This leads us to their second major innovation, a dual environment reinforcement learning framework for training. To get around those crippling scalability and cost issues of only trained in the real world, they first developed a high-fidelity simulated environment. Yeah. Think of it like a meticulously crafted offline Wikipedian knowledge base. A vast, controllable, and consistently reliable sandbox. This allows for rapid, low-cost experimentation, efficient data curation, basically a stable platform where the agent can learn the fundamental policies without the real-world risks or the huge financial burden.
Like a pilot in a flight simulator. They can rack up hours learning the basics before touching a real plane. Safe, controlled.
Exactly like that. And crucially, before hitting this intense RL training, the model also goes through what they call an SFT cold start,
SFT.
supervised fine-tuning. It means it gets a strong initial policy, a good starting point from being trained on examples first. This foundation ensures the agent isn't just wandering aimlessly when it starts the RL phase, like a new intern getting an onboarding manual maybe.
Yeah.
It's vital for RL systems where rewards can often be sparse or delayed.
Got it. A solid foundation and then a safe sandbox. But training only in a simulation, doesn't that introduce risks? You know, the classic sim-to-real gap when it finally hits the messy open web.
That's a very valid concern, and they were acutely aware of it, which is exactly why the second part of their dual environment strategy is so critical. For the final high-stakes policy training, the agent transitions to a robust, managed, real-world environment.
Managed real world. How does that work?
It wasn't just unleashing the AI onto the internet. It involved architecting this unified tool execution interface with systematic, almost military-grade management of external APIs. We're talking handling massive concurrency, building in fault tolerance with QPS constraints, queries per second, making sure they don't overload external services like search engines. Plus, sophisticated result caching, automated timeouts and retries for flaky connections, even switching to backup data sources if a primary one fails. This meticulous engineering ensures an exceptionally stable and reliable learning environment. It effectively prevents that data contamination we talked about, which could otherwise mess up the sophisticated policies the AI is trying to master.
So it sounds like they basically built a highly resilient operating system just for their AI agent, so it could explore the internet without crashing and burning, making sure the real-world chaos didn't undermine its learning process.
Essentially, yes. And it's a huge achievement in systems engineering. What's really fascinating, though, is how these two elements, the smart data from SailorFog QAV2 and this dual environment RL training, aren't just separate steps. They're integrated into a symbiotic feedback loop.
A loop. How so?
Well, this dynamic mechanism lets the system synthesize and filter high-quality data based on the actual dynamics of its training. So it continuously refines its policies, and that, in turn, improves its ability to generate even better data.
I see. It's a closed loop. The data improves the model, and the model helps generate better data, a virtuous cycle of intelligence.
Exactly. And it's worth mentioning they adopted the React framework as their agent's foundation.
React. Reason and act.
Yes, it's a method where the agent interleaves reasoning steps with acting steps, so it can dynamically plan and execute tasks. Choosing this, a sort of general scalable method, really speaks to the bitter lesson idea from Richard Sutton.
Right, the idea that general methods leveraging computation often win out over complex, hand-engineered designs in the long run.
Precisely. Their agent's toolkit includes standard things: web search, visiting pages, Google Scholar for academic stuff, a Python interpreter for running code, all leading to a well-reasoned final answer.
Okay, so the big question. Did this whole meticulously designed pipeline, with its smarter data and robust training environments, did it actually deliver? Absolutely. Trained on the Qwen 330B A3B model, that's the 30 billion parameter one, with an extended context length of 128,000 tokens, which means it can handle a huge amount of information at once. WebSailor-V2 achieved some truly eye-opening results.
The results, yeah, they're pretty compelling, especially on benchmarks designed specifically to test these deep research capabilities. On complex ones like BrowseCompEN, WebSailor-V2 scored a strong 35.3. On the Chinese version, BrowseCompZH, even higher at 44.1. And notably, on Humanity's Last Exam, or HLE, which is really engineered to test deep academic and logical reasoning, often needing synthesis across multiple fields, it hit an impressive 30.6. Those sound like significant scores, not just small bumps.
No, they represent a genuine leap.
But here's the kicker, right? And this is what seems truly remarkable. Their 30 billion parameter model significantly outperformed all existing open source agents, and it even surpassed the much larger 671 billion parameter DeepSeek v3.1 on both BrowseCompEN and HLE. We're talking a model that's over 20 times smaller, achieving superior results.
That's like a nimble scout drone outperforming a giant satellite, isn't it?
It really is. It makes you ask, how did they pull off that efficiency?
Exactly. And the implications for making powerful AI more accessible? Well, they're huge. Smaller models need much less computational power, fewer resources to train and run.
Absolutely. And this outcome strongly validates their core hypothesis, which was basically that equipping a model with exceptionally strong information retrieval and synthesis capabilities can profoundly enhance its logical reasoning. It allows the model to truly reason over externally acquired knowledge rather than just relying on what it learned during pre-training.
So it's leveraging the tools better.
Much better. They also showed highly competitive performance against leading proprietary systems, like OpenAI's DeepResearch, on various benchmarks. WebSailor-V2 even got second place on the tough DeepResearch bench, scoring 48.9. That was just shy of Gemini 2.5 Pro DeepResearch's 49.7.
So really close to the top proprietary systems.
Very close. And the small gap they suggest comes from their strategic focus. They prioritize a core information retrieval and intelligence synthesis over, say, the stylistic quality of the final report or more creative output.
That makes sense. Focus on the core research capability first. And it's probably worth circling back quickly to that SFT cold start phase we mentioned earlier. Giving the model that strong initial policy through supervised fine-tuning before the intense RL training, it seems like that acts as a crucial guide, right?
Absolutely essential. It's like giving that new intern not just the manual, but a mentor for the first few tasks. It ensures the agent doesn't just wander aimlessly, especially when rewards in complex multi-step tasks can be sparse and delayed. It needs that initial direction.
Okay. So the overall results are impressive. What about the learning process itself? Did they find anything interesting in the training dynamics?
Oh, yes. Diving into the training dynamics gives even more fascinating insight into how WebSailor-V2 actually learns. The training reward, when they plotted it, showed a clear, consistent upward trend. That's a strong sign of effective, sustained learning.
Good sign.
But what's really compelling, and this is highlighted in Figure 6 of their paper, is that the learning patterns were distinctly different for difficult versus simpler benchmarks.
Hmm.
Well, for the really challenging tasks, the RL process actually seemed to expand the model's fundamental problem-solving capabilities. It led it to discover genuinely novel strategies, like it might learn to combine tools it hadn't combined before in new sequences to extract information it couldn't get otherwise.
So it got genuinely smarter on the hard stuff.
It seems so. But for simpler tasks, the RL primarily enhanced sampling efficiency,
Sampling efficiency, meaning?
meaning the agent learned to more reliably find the optimal path or the correct answer on its very first attempt. It reduced wasted effort dramatically.
Ah, okay. So that raises an interesting question for anyone building AI, right? Does the AI get fundamentally smarter or just faster and more efficient? It seems for the really tough problems, it genuinely gets smarter, finds new ways to solve puzzles. But for easier tasks, it mostly refines its existing skills, becomes more reliable, more efficient.
Exactly. And that distinction has real implications for how we design and evaluate future agents. Another key observation, this was in Figure 7, was the consistently high policy entropy maintained throughout training.
Policy entropy. That's technical. What does that mean, simply?
In simple terms, it measures how unpredictable or exploratory the agent's actions are. High entropy means the agent keeps exploring various options. It actively avoids settling too early on just one narrow, fixed way of doing things.
So it stays curious, flexible.
Yes, exactly. And this sustained exploration, they believe, is largely thanks to the inherently non-stationary nature of the web environment itself. Observations from web tools are constantly changing, right? The web isn't static. This prevents the policy from getting stuck in a rigid state. It forces the agent to remain highly adaptive.
That's interesting. So the chaos of the internet actually helps keep the AI flexible, prevents it from getting stuck in a rut.
Seems that way. And they also clearly showed the power of increased context length. WebSailor-V2 significantly boosted its context window, from 32,000 tokens up to 128,000. That lets it process way more information at once, like giving the AI a much bigger working memory.
And did that help?
Definitely. Their analysis, in Figure 5, showed a clear positive correlation. Longer context meant better accuracy. But here's an intriguing point. Even at the shorter 32,000 token context length, their 30 billion parameter WebSailor-V2 model still significantly outperformed the previous 72 billion parameter WebSailor-V1.
So even with less working memory, the new version was better.
Much better, which powerfully highlights that their improved data generation and training pipeline had a more profound impact on performance than just increasing the raw model size or context window alone.
So it's not just about building bigger brains, it's about building smarter, more efficiently trained ones. The whole system matters.
Precisely. So to kind of bring this deep dive to a close, the pioneering work by Quan Li and the team with WebSailor-V2 offers a really powerful, maybe even counterintuitive insight, creating these high-quality, truly capable agents for deep research. It's fundamentally a complex system engineering challenge.
System engineering.
Yeah.
Not just algorithms.
Exactly.
Their findings strongly suggest that high-quality, intelligently structured data and a stable, robust training environment, well, they're demonstrably more critical than the specific reinforcement learning algorithm itself. That kind of flips some traditional thinking, doesn't it? It emphasizes the scaffolding, the environment, maybe more than just the core learning engine.
Yeah, it really does. What truly stands out to me is how they focused on solving those foundational problems, not just tweaking the agent, but really rethinking how it learns, creating smarter, more challenging data that actually mirrors real-world complexity, and building that training environment that's resilient enough to handle the internet's inherent chaos. It genuinely redefines what many of us might have thought was the primary bottleneck in developing these intelligent agents. This work provides incredibly valuable insights for anyone looking to build the next generation of truly intelligent, autonomous agents. Indeed. And that makes you wonder, doesn't it, if the quality of the data and the stability of the environment are truly the biggest drivers here. What vast untapped potential lies in refining these foundational elements across other diverse AI domains? Beyond just deep research, the implications could be immense.
A really provocative thought to end on. Okay, that's all for this deep dive into WebSailor-V2. We hope you gained some valuable insights into the cutting edge of AI agent research. If you like the content, hit like and subscribe to the AI Checkpoints for more deep dives into the world of AI. See you next time.